But welcome to our weekly meeting, the Physics and Astronomy Club meeting. My name is Nate. I am the president. For those of you who might be here visiting from another chapter, thank you for joining us today. Today we have Emily and Kelly, who are engineers from Whitewater West, which is an engineering firm, and you guys are in British Columbia, right?
Yep.
Yeah.
Yeah. And they specialize in designing water slides. So we thought this would be kind of a cool, like niche topic about, one of the industries and fields that are out there that employ physics and engineering into, kind of a product and service that maybe most people don't associate with physics and engineering. So again, it's 12:03. If people join late after this point, then that's fine. But I guess I'll go ahead and turn it over to Emily and Kelly. And thank you again for being here and doing this presentation for us. We really appreciate it.
No problem.
Thanks. Yeah, thank you very much for having us, and thanks everybody for joining. My name is Emily Colombo, and I am the Vice President of Strategic Partnerships at Whitewater. I've been at Whitewater for about 8.5 years, and I did many years in design, and then I've kind of moved a little bit to the sales side, but I still do design because I like it. So it's always a fun challenge with different complicated sites, and the better the project, typically the more complicated it is, which Kelly can attest to.
Yeah.
And so I will allow Kelly to introduce himself, and then we'll give you an overview of Whitewater.
Okay. Thanks, Emily. My name is Kelly Williams. I'm a professional engineer. I manage the team we call water slide engineering, and that is the team at Whitewater that does the slide dynamics and the analysis of body motion and water flow and all the stuff that makes the slide work and work safe. My history is a pretty mixed bag. I started with designing mountain bikes. I've done laser imaging systems. I've done industrial automation. I've done data recovery systems. I did a stint with US military UAVs. And I did automotive systems. Now I do water slides. So it's all over the map. But I've been with Whitewater for 5 years and I love it. Okay. So over to Emily.
Yeah, thank you, Kelly. Whitewater is the largest designer and supplier of water parks in the world. And we have been around for 40 years making water slides. They were pretty bad when we started, but they've gotten a whole lot cooler since then. So we are, if you want to go to the next slide, Kelly, we are very global. So we do projects in almost every corner of the world. We've got 6 regional offices, the bigger ones being in Shanghai and Dubai. We do over 200 projects a year. We've got 100 products, which is a lot of different kinds of water slides, and about 600 employees. So we're a big company and do some pretty awesome projects. This is one of my favorite slides. It is obviously a map of the world and shows projects that we've done over the last 40 years. And you can really see that we have kind of gotten to each corner of the globe. Kelly did mention that we need to do a project in Antarctica to really round out our portfolio. Yeah, we do.
Oh, sorry.
Oh, good. So we do projects in Russia, in Estonia, in Wyoming, and kind of everywhere in between. So I will go through kind of 5 of kind of prize projects that we've worked on over the last couple of years. And as I said before, the more beautiful they are, typically the more difficult they were to build. So I'll give you a little bit of a sneak peek on some of the challenges that we went through and some of the obstacles that we overcome. So this is a project that is very, very gorgeous. As you can see, everybody always says, well, that's a rendering, but it's a real photo of the site. It really looks like that. So it's in the Bahamas. It's a 135-foot tall tower in a 100-mile-per-hour wind zone, which is a pretty extensive wind loading on a tower that's covered in essentially a sail. So the footing for this thing is 90 feet by 90 feet by 2 feet deep, and it's 20,000 cubic feet of concrete to hold it up. The other interesting thing is there's no concrete that is available on site. So everything had to be shipped in, and there was no port when we were building, there was no cranes on site. So we really had to make it happen with the Royal Caribbean team. Also in the background, there's another award-winning project which we worked on, which is a Master Blaster, which is one of the rides that we'll go through a little bit later, and it loops around the outside of a ship. So it's the longest water coaster on a cruise ship. The next project that I'll show you is the Disney Aqueduct. There's a famous kind of moment in our history where we were suggesting that they build this water slide out of what we call translucent fiberglass, which just uses a different kind of translucent matting that allows light in, but you can't see it. And the Disney architect said, no, I want it like a water glass. And we had no idea how to do it. We didn't know how much it would cost. And we ended up building this project out of acrylic, which is a very thick material. Each of these pieces is about 1,000 pounds, and that's on the top of a cruise ship, which is, there's 18 floors, I believe we looked at yesterday, and the whole thing, swells and it vibrates. So we had to figure out a way to allow the acrylic to expand and contract, and that's where you can see those rings there, because the acrylic, if it hits each other, it'll crack. So it was an amazing project for us to collaborate with Disney on. Aqua Park Geneva is a kind of fun one for me personally. This is a project we worked on like 25 years ago, and we built a bunch of slides in Switzerland, and they're connected to an indoor building, and it's, it doesn't look very nice. I can attest to that. So they said, we want to take out the yellow slide and put in a new ride. And so I flew there and I walked around, and I, tried to visualize how we would fit a water slide in there. The other thing that they didn't want to do was close the park. So they wanted to keep it open while they were taking the other slide out and putting a new one in. So after walking this site, I came home and stayed at the office very late and figured out 4 options for them. You can go to the next slide, Kelly.
Nope.
4 options of rides that we thought could fit. We did a site survey with them, modeled up their existing rides, and they ended up choosing the top right. And then you can go to the next slide. And this is their marketing of it. And then this is the slide actually built. So the closest clearance from the new slide to one of the existing slides is like 3 inches. Like they were like pushing fiberglass out of the way to get it to fit in there. And we're glad that they had a good site surveyor to ensure that it was actually correct when we got on site. The next one I feel like I must show you is Roko Island. Roko Island is a project in Japan, and Whitewater has a long history with doing projects and doing work in Japan. We started, it was our first international foray into the Asian market. We met a Japanese man, and then we started building water slides with him. And they wanted 100 slides off of one tower. And we said, like, that's way too many, not possible. So we ended up doing 50 of them. And this entire thing was designed on onion paper. Like, we didn't have any computers at the time. It was all just a big stack of onion paper slide path designs. And then this entire island, Roko Island in Japan, there was an earthquake and it broke all of the foundations. All of the mechanical systems were ruined. Everything around it was ruined, and the water slides were still standing tall. And so there was an agent in Japan that started taking these apart and trying to sell them to parks as like secondhand slides. And we had to call him and kindly ask him to stop doing that, because he was eating our lunch and we couldn't sell anything because he had all these used slides on the market. It's crazy. Go to the next one. And then I did want to, so this is this is kind of where it all culminates in craziness. This tower is 260 feet tall, and it is has slides that go from level to level where you can take an elevator up the middle of it and choose where you want to start. And then you get to another level and you're in your raft and you can decide if you want to go one way or another. So it's like a choose your own adventure slide all the way down. And then there's a ride that goes from the very top all the way to the bottom, which is like the longest slide of all time by far. And this project has been kind of conceptualized for the last maybe 7 years, and we saw renderings of it, and we had no idea if it was ever going to get built. And they are well on their way to constructing this. We've got fiberglass on site, and we've got steel on site, and they're opening for the is it the World Cup? Maybe this. I might be wrong there. But if you want to go to the next one, Kelly. So here's a rendering of what it's actually going to look like. You can back the other one. So here's a rendering of what it's going to look like. It's
sorry.
That's okay.
There we go.
Okay. So it's on a man-made island, and there's a train that you line up in the rest of the park, and then take a train over to the island, and it takes you to the central core where there's food and washrooms and everything within the central vertical water park. And we had a lot of questions when we were starting to work with the client on this. How are we going to ventilate the slides? It's in Qatar. It's 100 degrees, and these slides are long, and they're going to be sun beaten all day, and they're going to be hot. It's a big one. How are we going to get water to the top? How are we going to support the slides? This blue slide here is 55 foot across, and that's just hanging off the top of a tower. And how are we going to build them? I mean, there's been a lot of questions, but we're getting through those, and the project will probably be open within the next kind of like 8 months. I think November is when they're looking to do that. Alongside this massive vertical water park, there's also an entire other water park that is just kind of flying under the radar because everybody's looking at this. If you want to pop to the next one, Kelly, you can see that. So here's the entire park that they're building, and then the train that goes out to this man-made island. They also have other rides like hanging out over the ocean, and only in Qatar. And here is a picture of how they're progressing through that. So they built the island, built the central core, built the elevators, and they're starting to build all of the structure that we're going to tie all the slides into. And there's about 1,000 people on site trying to get it done right now. So as you can see, we work through a lot of kind of different places and different concepts, and we come up with new rides for people that want to make their mark on the water park industry. And that's what I've got for you today. Now Kelly's going to go and tell you a little bit more about how things are made.
So I like to call this the geek stuff. I was saying to Nathan before, I'm an engineer, you guys are physicists. This is like orangutans and gorillas. Choose which one you are. We're very, very similar. We used a lot of the same theory. So I'm going to go through how it is our team goes about making the slides safe. I tell people all the time that just because water slides are fun, it does not mean they're easy to make. Very simple. So this, when we get students coming in, I'm going to start from square one. Grade 11 physics. Gravity. It's the most reliable force in nature. The sun pulls really, really hard on the earth. The earth kind of pulls on the sun. Same thing on smaller scale. It pulls on people. F equals MA or mg. But this is how, like in basic principles, how of course we work with the body flying down the slide. The force of gravity is split up into two vectors. Pretty simple stuff. But it's actually it's more than that. You're dealing with something in what you would call a cylindrical coordinate system, where you've got the basics of a body going down the slide, but you also have to consider the rotational component. So what about oscillations? Oscillations can be very dangerous if you sweep one way on a slide and then suddenly sweep the other way just as they're oscillating to the top, and suddenly the slide sweeps away, then you can send someone airborne into the far wall. And that is like one of the design features or the design criteria that we follow. It's called switchback analysis or oscillations. So let's see, next slide is how do we actually do it? We have two proprietary in-house pieces of analysis software. One is a very detailed simulation system where we have a liquid cooled supercomputer not far from me that runs simulations all day. And it can take half an hour or more to run a simulation on a single slide. So this is an enormous amount of data being run through and analyzed. And what it's really doing is it's breaking up this slide component. This one here is on the left is simplistic. You could solve that with a single calculation. On the right, it's a very complex and sweepy, curvy shape. And so what it'll do is break that up into, I don't know, 10 million parts. A lot of parts, and each one of them is considered like, you know what the energy state is coming in, you know what the energy conversion across that element is, so you know roughly what the energy state at the exit is. And the roughly part is where the challenge comes. We have studied and studied and studied this for, well, over a decade. 5 years before I started working here, we started working on simulation analysis, and it allows us to have a fairly high degree of precision of predicting how a slide will work with a body or a tube or a raft. I will show you some examples later. But the common assumption, as I said, water slides are fun, therefore they must be easy to make. What we're really looking to eliminate are three conditions. There's catching air. You want to give the illusion of someone catching air, but that doesn't mean they're actually losing contact with the slide. You want to make them feel light. And that is a foreign feeling for them. You also want to avoid giving excessive G-forces. Various regulatory bodies around the world have different levels of G-forces they allow you to work to. But that's one thing. There's the reality is that, generally speaking, no matter how much water you put in a slide, if you exert more than 3 Gs on a body going down the slide, you will give them skin burns, no matter how much water is in the slide. So that's kind of a pretty hard limit to work to. And then, as I said earlier, there's poorly timed oscillations. If you do it just wrong, you can give someone a very bad day. And we pride ourselves in the depth of analysis and utilizing the work that we've put in for the last 10 years of fine-tuning these tools. So how do we go about designing the ride experience? I like to say we design the experience, and that results in the water slide design. So what we will do is Emily will be dealing with an end user or a client, and they will say, I want a slide that's steep and fast, or I want one that oscillates and lets you feel light, or one that really whips you around a corner. So we can design, okay, this is almost the story of the ride. And then throughout, as you're designing it in our design software, just SolidWorks, we will look at it and we can identify at any given point, okay, at this particular point, I'm hoping you can see my arrow, the velocity at that point, our simulation package can predict that velocity to a fairly high degree. And from that, we know the grade that they're operating at. And from that, we have curves generated for all of our slide parts that show what you see here. The green area is 0.4 Gs or more. So I've left the velocity off just to, I don't want to get too deep into the hard numbers. I just want to show the theory here. The higher the velocity, the less steep you can tolerate before it winds up getting lighter and lighter and lighter. So the green area is going to be a relatively benign but kind of fun slide experience. The yellow area is what I call the sweet spot. And if we map the velocity from our model to the grade at that particular spot, that's where the little bang icon is. And so if that exists in that yellow band, that tells me that the rider is going to experience between 0.2 to 0.4 Gs. And that is a sweet spot because that will let someone think that they've caught air. Because that is 0.2 Gs is very, very light. They don't realize that they're still touching the slide at all times, but it is such a foreign experience that people think it's something different than it is. So I like to say that we design our slides to create safe anxiety for our riders. And what I mean by that is that they can go to a water park and see an aqua loop and look at this thing and think, oh, I'm not sure if I want to ride that. It looks pretty scary, but that's a challenge for them. They will look at that, and by the end of the day, they will have worked up the courage to ride the thing and left feeling like they've accomplished something, or they will leave frustrated because they couldn't build up the confidence to ride it and they leave. But in both cases, they want to come back and do it. So there's like a repeat. If we do our job well, that's the result. So yeah, predicted velocity versus grade. This is how we design the experience and we tune the experience. And so, like I said before, every one of these sections has these are all different curves. They're very slightly different. So these are the convex parts, and I'm talking mainly about water coasters. This is one section of our product matrix, but the concave parts at the bottom of a drop where it comes down a drop and goes up a hill the other side, we can also look at, these are the G loadings that you meet, and the top line is 3 Gs and the bottom line is 2.6 Gs. CSCI is the Chinese regulatory group. ASTM is generally everywhere else. So we can predict based on, sorry?
One thing to note is if anybody ever applies to Whitewater, we will ask you about the G-forces allowed on a person in an interview. That's a question that comes up all the time. It's always at the end. I got asked, I think I guessed 8 when I first started.
So I gave away the answer.
Yeah, you gave away the answer. I mean, you can also Google it, but it is something that we ask kind of tongue in cheek, but no. Yeah.
Okay. So yeah, these charts are showing what the body will feel like as it's feeling light, and this chart here for multiple flumes is going to show what the body feels like as it's feeling excessive G's, about being pushed around a corner or through a drop. And okay, so those relate to a product we call the Master Blaster. It's a fairly evolved product. It's been around for quite a while. It's termed as a water coaster. It's basically a roller coaster without a roller coaster body. So you start, this is the current world's tallest water coaster. It's in Galveston, Texas, at a park called Schlitterbahn. This was the first project I went to when I joined Whitewater. I was the first Whitewater employee to ride this thing, and my heart was in my throat. I didn't know what I was getting into. It's an exhilarating ride. This initial drop is on the order of 10 meters or so about 30 feet. It's so about 30 feet. It's quite a drop. At the bottom, I'm not sure how many feet per second, but you're doing between 13 to 15 meters per second. So it's fast. You feel around 3 Gs at the bottom, and then you get pushed up this other side with 2 water jets that are putting about 1,500 gallons per minute. And you can see the result on the left side. The water thrusts you up the hill. And this, as I said, this is a fairly evolved product. It's been around for quite a while. So there's the Galveston, Texas in the upper right. And then this product is also used in what you call a transportainment system, where you can have what we call a lazy river going all the way through a park. And occasionally there can be a split off from that lazy river that goes to a ride up conveyor to a slide like what you see on the left, where that slide, due to the thrust performance of the slide design, that slide is actually net gain. It's going uphill. It ends a full story higher than it started, which is a bit different for when you think about water slides. It's actually pushing you uphill, and you gain elevation. And then you go into this this tower in the back, where it allows you to split off, and it's like another version of a snakes and ladders game. You can choose which way you go from there, and there's other slides in the background. It's a giant network of slides, but this is one of the main entries into that that pyramid. So this slide is in Dubai, at the end of the Jumeirah Palm Island. It's called Atlantis Dubai. And then that same product, the same basic product, the same product concept, can be used on a smaller, very cost-effective version where it's high throughput, the same exhilarating drop, but low cost, low maintenance, and so on. So this is the very minimalist approach to providing virtually the same product. Okay, but then a lot of people ask, what's different about water slides versus versus roller coasters? And many people told me when I joined Whitewater that actually designing water slides is more difficult than designing roller coasters, because for one thing, in a water slide, your body is going to follow a certain velocity profile and a certain oscillation and so on, but it follows that on its own. In a roller coaster, your trajectory is defined for you. The only thing left is the velocity along that trajectory, which results in g-forces. So basically, we are limited to the green area and the yellow area, and the red area is a no-go zone, and the white area is absolute no-go zone. The red area was, as I said before, or as I showed before, 0.2 to 0 G. So that's getting pretty dangerous in terms of becoming a projectile. The white area is absolutely a projectile. You have caught air. And so we avoid that at all costs. However, in a roller coaster, it's different because, as you can see, these people are strapped in. There's nothing, there's very little that can happen to them. So I'll get to the other physics and analysis that affects them here. It's not all just about g-forces. There's, of course, position, velocity, acceleration, and jerk. So these are all derivatives of one another. And jerk is the one that many people don't know about. And actually, it's I tell my kids all the time, do you know where the name of Rice Krispies came from? Position, velocity, acceleration, jerk, snap, crackle, and pop. In my past experience with industrial automation, we went as far as snap, crackle, and pop to get like sub-micron tolerance positioning of servo systems and so on. But in water slide design, we handle position. That determines the launch frequency, how many rafts you can put into a slide design and guarantee that they will never collide with each other. We call that zoning a ride. And then velocity, that applies in safety codes and slide design. Do you want to make it fast? Do you want to make it slow? Do you want to make it exciting? Yada, yada, yada. And then acceleration, preventing airborne conditions or excessive g-forces. But that's not everything. Jerk is important in terms of avoiding whiplash. And every time I talk to an engineer or a physicist, I always throw in this gratuitous geek joke. I've got this written on my wall right beside me, and this says, "Don't be a jerk." So what's really going on in the background is we all love calculus, right? Right? I hope there's some heads nodding. We all do calculus. I hated it when I was in university, but you have to do it. So what's really going on here is an energy balance, where you're trying to determine at the end of an individual element along this slide, what's the final energy state of that person? And then this could be a person or a raft. So you start with the initial energy from the previous element. Then you have the delta energy from gravity, which is the line integral from A to B of some function of mg sine the angle. Then there's the delta energy due to the person or the raft friction. So that's due to the line integral from A to B, friction coefficient, normal force. So that is something related to sine theta, plus something to do with the flume shape. And if it's a raft, there's going to be some impact of the pressure or the stiffness of the raft. And then there's the delta energy due to drag, which is the line integral from A to B of some function of, this is the body pushing water out of the way. So velocity of the body versus the velocity of the water, they're going to be different unless they've reached steady state. It's also a function of the flow of water. How much water is there to push out of the way? And the drag coefficient of the body going through the water. So that drag coefficient can obviously change radically from a 10-year-old kid to a person like myself. And then, of course, if there's something like those master blasters you saw earlier, there's thrust components. So the delta energy from thrust is the line integral from A to B of a function of the velocity of the body, the velocity of the water flowing in the slide, the flow rate of the water flowing in the slide, the velocity of the water jet, the flow of the water jet, plus some thrust coefficient to determine how effective that water is at pushing that said raft shape. And all of these things are very non-linear. So this is why I say we've been working on this stuff for over a decade. And this is really just lifting the hood and letting you see the engine. There's a ton of detail in this. Okay. Let's talk for a second about different types of water jets. When you've got a large, what you see at the bottom in B is much like what we have in our master blaster, which is a large flow of water. There's a large flow rate. It's, you saw in the picture, the raft, there was a lot of water behind that raft, but that's high flow rate, but low water velocity. It's like a log floating down the river. If the log is stationary and the river's moving, the river will push the log. But what happens is if we were to use a whole bunch of really high velocity water jets, then what you'll have is that there's the differential between the velocity of the water is exceeding the velocity of the tube to a point where the tube never catches up to the water. And so basically with high-speed water jets, the raft speed never approaches water jet speed. So the thrust is always maintained. The result is if you have a whole bunch of high-speed water jets pushing a raft that happens to be low weight, so a very small child, you can cause them to overspeed. They will accelerate continuously for a lot longer than a full-grown person like myself or Emily. And the net result of that turns into product robustness, where your weight envelope of your product gets smaller. You wind up having a smaller upper weight limit and a more conservative lower weight limit, because you know your product is only robust in this little area. Whereas in our case, we choose to use a lot of water such that the velocity of the water and the velocity of the raft are not far from each other in the end. And what that means is that as the tube velocity approaches the water velocity, the thrust tapers off. So it's self-controlling, and it's proven it in terms of the master blaster I showed you earlier. The weight envelope of safety and robustness of that product is actually very wide. So it's not overly sensitive to the weight of a person. You can put a very light person in, or a very heavy person, or two very heavy people, and the raft or the ride will not operate radically different than a very light person. And it's done that way by design. So there's a lot of physics and detail in these things.
It's a very complicated issue for us as a company. We've got rafts with 6 people allowed in them. And, that could be anywhere from, 6 young kids at the age of 6 years old that weigh, 45 pounds each. I don't know how much a 6-year-old weighs, or you could have 6 grown men. We're doing a project at a football Hall of Fame, and you could have 6 linebackers in there. So it really adds a dynamic and an element that we have to account for. Whereas on roller coasters, that isn't as much of an issue. Seating position within the raft also can change how the raft oscillates. It can rotate differently. If there's one very heavy person in it, it can have the whole ride operate differently. So it's a big component of Kelly's difficulties.
It's a major source of my stress.
Yes.
It's a good stress.
Also on body slides, sorry to interrupt you, Kelly, on body slides, I've ridden a lot of water slides, and you can go slowly sitting one way. And if you get up on your heels with your shoulders, you can go 2 or 3 times as fast. So rider position, the other thing that's an aspect for us is different materials of bathing suits. Like in the Middle East, we do a lot of water slides there, and they wear what they call burkinis. And it adds a lot of drag to the rides, and it has people going a lot slower than they would in a typical water slide where people wear bathing suits. So there's a lot of different elements when it comes to materials, weather, different cultures.
Okay, so the other simulation package we have is, again, it's in-house, but it's based on a SolidWorks backbone. We will see a slide in a wireframe like this, and the first step is we will run a simulation, and the line you see in the middle is the center of trajectory, the center point of the raft as it goes down. It shows the motion of it going down all the slide. And so the entry box is the absolute top, and where the arrow is pointing to with the raft is currently sitting just before the pool entry. And there's a bit of a drop there right before the pool entry. And generally speaking, we don't like to see the waveform that we see there in that red oval right before the pool entry. That means it's oscillating while it's dropping. And that can inherently cause G-forces, airborne conditions, jerks, head bonks, that kind of stuff. So the first step is to detect those. We have some relatively rigid standard design practices in this company to flag this and say that is not good enough. So the slide will not proceed until we mitigate that. But just to show the complexity of the challenge, we take that. The step 2 is refine the slide path, and you can see the slide path looks the same, but there's very subtle differences. The problem was detected at the end, but you can see that where it says step 2 refine slide path, there's the arrow to the right of it showing where we started to mitigate the problem is far upstream. You can see that it's the first corner in that red highlighted area is different than the left image. So we refined the entire slide path there, and you can see the result. That is step 3, showing the optimal oscillation into the pool. It's within the parameters that we have deemed to be reasonable and we follow in the company. And at that point, we release the slide to be built. Okay, but that's all wonderful. That's great. But how often do you rely on software as if it's gospel? And that's where it gets interesting. This is how we do it. So with both proprietary analysis tools, we don't treat them as perfection. They're continuously evolving. So we've done this for a decade. We're going to keep doing it for a decade and more. Because when we come to a site, this is what you see on the right is a boomerango. It's actually installed in Japan. And we take a drone and hover it at roughly the same perspective as what we can achieve by looking at it in the simulation package. And we will overlay the trajectory and kind of do a quality audit, not on the slide, but we do a quality audit on the software to determine, okay, how close is the software to what really happened? We, as it says on the slide here, it says the predicted simulation video. So this was done more than a year in advance of actually building it. And then we would get the actual, and then we overlay them on top of each other. You can see the raft position. You can see the raft position. It matches. So that, in a nutshell, is how we do our jobs. That's how we create safe water slides. It's all based on physics. And I was actually very excited to come and share this with a body of physicists, because I find this stuff absolutely fascinating. And with that, we wanted to conclude with a couple of stories. Emily, do you want to go first?
Sure. We wanted to tell you kind of how we ended up where we are, and I think we both have some pretty strange stories.
Yes.
And I don't know where most of you are in your career, whether you're getting into the job force or doing secondary studies or just brushing up on your physics masters. But I was a fresh graduate from Queen's University in civil engineering, and I was working for Lafarge Concrete. And I went to a water park for a birthday, my birthday actually. And we were standing at the top of a tower, and a friend of mine said, "How do they know that people are going to go up and all the way around that slide?" And it was one of the slides that you can see there on the left, the one that goes upside down. And I said, "You know what? If you gave me a textbook, I could probably figure that out." And I went home and I Googled who makes water slides, where do water slides come from? And I gave notice on Monday to Lafarge. And I put my resume into Whitewater. They did not hire me, and I was just appalled. So I flew to a trade show in Las Vegas and I walked up to the Whitewater booth and said, you know, I'm passionate about the industry and I'd like to work at your company. And they said, "What do you want to do?" And I said, "I'm not sure, but I know that I want to work for you." And I moved about 4 days later from Ottawa, which is on the east coast of Canada, to Vancouver on the west coast. I'd never been to Vancouver. I'd never didn't have a house. I stayed in a hotel close to the office, and found a home in slide path design. And since then, it's been 8 wonderful years of seeing the world, seeing water parks, riding water slides, going to roller coasters, talking to people from Disney and Universal about very comical, everybody's trying to learn, everybody's trying to grow, and everybody's trying to move the industry forward. And sometimes that ends up in some pretty awesome mistakes, but it's a really cool industry. And I think that the genesis here is just that if you're interested in something, go do it. Somebody's got to make it, somebody's got to engineer it, and it's pretty cool.
Yep. My story is similar but a little different, and the photo on the left is actually quite meaningful to me. That purple slide that Emily was talking about, I was standing 5 feet from that when I effectively the point at which the spark happened that I could get this job. I've worked, as I said before, I've worked in multiple companies, multiple industries. I've actually been with several companies that have gone bankrupt or gone through aggressive takeovers, and like I've been through some rough experiences with companies. And I had a safe job, but I turned 40 and I decided that I had a midlife crisis, I call it. Most people buy a sports car. I decided I was going to quit my job. I had a good job, safe job, it was good people, but I thought this is not it. There's something else. And I decided I was going to quit my job and do a master's of business administration. I did the MBA and I quit my job. But the path to getting the job was interesting. I saw an online application to Whitewater, and I clicked on the link, and the link had expired a day before I got to it. But it still said, submit your resume anyway, and we will keep accepting applications until we fill the position. And so I submitted my resume, didn't hear a thing back, nothing. I was very frustrated because I thought, this is it. This is what I think I want to do. And then a couple of weeks went by, and I still didn't hear anything. I had no way to follow up, and I had a really frustrating day at work. And I said to my wife, like, no, nobody has this much bad luck in their career without it evening out, and it's going to come down to a decision. And if I make the decision the right way, it's going to change my life. If I don't make the decision, I'm going to regret it forever. So just out of sheer luck, my family and I took a road trip up through BC over into Alberta to this water park. This was one of the stops. This is West Edmonton Mall, largest indoor water park in the world, I believe. And I was sitting right at the top there, by the top of that purple slide. My daughter's about to go down a slide, then my wife, then me. And I looked to my left, and there's a water slide under construction. And I thought, oh, I wonder if this company, Whitewater, did that. So I start looking around. I'm soaking wet in my shorts. And I see a drawing with the Whitewater logo on it, and it piques my interest. I said, look, to my wife, I said, look, that company's doing this. And I look around and I see these 2 guys walking up the staircase in business casual. One of them's got the Whitewater logo on. And so I said to my wife, this is it. This is the decision. And she says, what do you mean? And then she says, you're not going to interrupt him. I said, yeah, I am. So my daughter goes down. My wife says, whatever. And she goes down. And then they're both waiting for me at the bottom. And then all these other people start coming down the slide. Where's Kelly? I interrupted him. I said, my name's Kelly. I applied to your company. I didn't hear back. I would like to be interviewed to work at your company, much like Emily did. And I was wondering if I could have your business card so I could follow up. I really think I deserve a follow-up meeting to discuss maybe how I could work at your company. And so I connected with the person. His name is James Hansen. He's our director of project services. And we connected on LinkedIn, and he started sending me job opportunities. I started applying to more and more and more. I think I applied to 7 job opportunities before I finally got in, but it took about a year of persistence. And that opportunity is what finally got my foot in the door. So he gave me his business card, and I finally came down the slide, and I tried to hold the business card dry as I went down the slide, and I yard sailed into the pool, got it soaking wet. And my wife looked at me, where you been? And I showed her the business card, and she said, oh my God. So that it was sheer luck, thousands of kilometers away from the office here. I live 10 minutes from the office, and yet it was deep in Alberta the spot where I decided that I was going to change something, and it resulted in a big change for me. So I guess the advice that we're both trying to give you is much like the image on the right. Often life will present in that image, it shows 5 options. There are infinite options for you. Don't stick yourself to 5 options. Make the 6th or the 7th or the 10th until you find the one that's for you, and then it'll change your life. So that's it.
Awesome, guys.
Okay.
Thank you so very much. I mean, I personally love both of those stories. I mean, that's essentially where it is that I'm at. I had a very safe, secure job, and it just, after working there for several years, I was like, man, this just isn't for me. So I quit my job, went back to school. So I very much identify with that particular path. But, yeah, thank you very much. We really appreciate it. We can open it up for questions now. If people have any. One just real quick thing I want to say, Kelly and Emily will not be able to speak to any particular safety incidences. If you have heard of anything in the past or whatnot that you feel like, if you have questions about the specific incident, that's not something that you can talk about. Other than that, I'll open the floor up for questions. So if anyone's got them, feel free.
I'm looking to see if anybody goes off mute.
I don't have a question, but I just wanted to say that your term happy anxiety put a smile on my face.
Yeah, safe anxiety.
Yeah.
Safe anxiety. It is
Yeah.
nice. That makes me think of the free fall slide, which is everybody knows that.
Yeah.
It's the, you sit in an entry box and it just kind of rolls away from you. And, we've been building that slide for 30 years and every park has one. It's either on a tower or it's the icon, like it, and it is the slide that you have to, we also have the ones where it's like a drop box where the floor drops out and you fall down. But I actually find the one where you have to do it yourself scarier, because you have to actually be like, yeah, I'm willing to do this, where the floor drops out, you kind of just put in and then it happens to you. But the free fall is definitely the safe anxiety.
It's interesting. My wife feels the opposite. When she climbs into a launch capsule, she experiences claustrophobia and total lack of control because it's counting. You're launching.
Oh yeah.
So both of them are totally safe. That's the point. But the other point is that it's not about, not every ride needs to be something that causes anxiety. That's kind of a vague assumption. Some just want to provide a fast slide that's fun, or
Yeah.
A droppy slide that goes around corners and goes around a bowl, or it's just an enjoyable experience. There's dozens of different experiences that we try to design in the slides. It's not all about anxiety, but those tend to be the icon ones.
Yeah. And you're absolutely right, Kelly. We often talk about the family of 5. You got to make sure that the park makes everybody happy, including, the 12-year-old that wants to ride that crazy tall free fall slide, or mom and me want to ride something together that is a nice experience where they can laugh and feel comfortable and safe. And it obviously depends on the demographic that the park is trying to target. We do a lot of work with Legoland, and all their rides are short. All their rides are within that 0 to 0.2% G-force. Like, they're not interested in the yellow zone or the red zone. They want everything to be really, really mellow, because that's their target demographic. And if they're marketing to young children and they make them happy, then mom will bring them back. And every parking lot every parking spot's a wallet, for sure.
And the other part of design that we haven't covered is there are users of the park that will never ride the slides. You can have a giant family that they bring their grandparents along, and the grandparents do not want to ride a 6-person boomerango. So in that case, what you do is you design the queue line and the supporting structure around, such that you can have great viewing angles. So a person who doesn't want to ride can still experience it by watching the rest of their family go through the ride or taking pictures of them. So queue line design, tower layout, and viewing angles and theming, all of that is encapsulated within the total design challenge.
Nice.
Any other questions?
Yeah.
Would you say that a physics or engineering degree is about comparable, or is one vastly preferred? Or
In this business, I think they're about the same personally. In this specific segment of our business, you need to have a very thorough understanding of physics. When it comes time to doing mechanical design of a water nozzle or something like that, then it's probably going to be an engineer. But that doesn't mean it has to be. Some of the best technical minds that I've met in my 22-year career now, some of the best technical minds that I've met are neither physics or engineer. They're self-taught technical. And that's in mountain bike design and automotive systems. And these are people that are the truest form of entrepreneur, and they just get it. They're technical minded people. So I don't think it's exclusive. I think being an engineer is kind of an easier way in, but not much more than physics. I think you put it this way, your resume would be looked at, that's for sure.
The owner of our company always calls himself an honorary engineer.
Yeah, that's valid.
Yeah.
He's an accountant.
Yeah, I mean, maybe there's some overlap there. Anybody else?
Going once, going twice.
All right, cool. Well, oh, Antonio, did you start me? Yes? No? Okay. All right. Yeah. Well, Kelly, Emily, again, thank you so very much. We really appreciate your time and really appreciate the presentation. It was great. Yep. Thank you so much for taking time out of your day to meet with us and to talk with us. We really appreciate it.
Great.
No problem at all.
All right,
thanks
guys.
for the invite.
Yeah, absolutely. Absolutely. I don't think we have any other like club business to talk about, like as far as the chapter is concerned. So we'll just go ahead and call it adjourned. Thanks everyone for showing up. Appreciate it. And everyone have a great weekend.
Okay. Yeah. Happy Friday.
Right.
Bye, everybody.
Bye, guys.
Thank you very much. Bye.